Okay, this is going to be on our mass spec parts of the Chemistry 729 course, and this is my introduction video to you all about what we're going to cover in the 3 lectures that I'm going to have. So this is just an introductory video to kind of give you an overview of mass spec, and then we're going to move into you reading some papers, and then I will post once a week for the next 3 weeks a video on the importance of some of the things. So what are you going to learn in this particular, so what will I learn? Very important question, right? And so this is not a course that is designed to be a structural elucidation course. So you're not going to learn how to determine structure from an unknown sample. We're going to assume that you have some information about what kind of samples you're looking at. So you're going to learn what we can get from mass spectrometry. You're going to learn which technique to use. And we have several mass spec techniques that we can actually use in our facilities. So excuse me for having to refer to my notes. And then you're going to also learn how to design experiments using mass spec. So we're going to teach you how to be a little clever using the mass spec techniques that we have. So those are the 3 main goals that I want you to leave these lectures with from this course. And again, just to emphasize, this is not a structural elucidation course. So none of the questions you'll receive on any of my assignments or the exams will involve an unknown structure. Okay? So what does MS tell you? Well, if you think about mass spectrometry is actually a very simple technique. And when you look at a mass spectrum, you have the mass to charge ratio on one axis, and you have intensity on the other axis. And you will see a variety of peaks within that spectrum. So I'm just drawing in some arbitrary lines. That's all you get from mass spectrometry, is you get the mass to charge ratio of analytes, and you get the relative intensities, of course, with the most abundant one being set arbitrarily at 100, and everything then is a percent of that most abundant peak. So it's a very simple technique in terms of what you actually get out of the experiments. But if you use some clever experimental design, so if you actually incorporate experimental design with this, you can actually convert this simple plot into some very, very useful information for your own research. And so that's what we hope that you will take again from this class. So some of the other things that this kind of information will give you, of course, you can determine the molecular weight of an analyte. Right? If you know the mass to charge ratio, if you know the charge, you can determine the molecular weight of the analyte, which also means as a result you can determine the atomic composition. So you can get a mass to charge ratio, you can determine the molecular weight, and then you can determine a small narrow set of atoms that will actually be assembled to give you that molecular weight. And as a result, you can also get some structural information. And you also get, from mass spec, very sensitive detection. So mass spec is one of the most sensitive techniques that we have available to us as chemists, and we can actually get sensitivities down to easily the femtomolar range. So you can get down to femtomolar with mass spec pretty easily, and so it is one of the more sensitive techniques that we have at our disposal. So what do we need to do mass spec? So what is necessary to actually get a mass spec of an analyte? So what must we have? Okay, so what do we need to have other than just an analyte? Obviously, you have to have something that you want to analyze. But there are a couple of things that, regardless of the mass technique or mass spec technique that you're using, you're going to have as part of the equipment. One of those is an ionization source. And so we've got to have that mass to charge ratio, so somehow we've got to take the molecule and ionize it. We'll talk a little bit about that. You've got to have a mass analyzer. You have to have some sort of detector. You have to have a data system. You have to be able to collect the data. And today, of course, that's a computer. And of course, all of this has to be under vacuum. So you have to have a source of vacuum, okay? And you have to have very, very good vacuum. Your vacuum source isn't just your typical rough pump that you might use in your laboratory to pull a vacuum on a flask. Those typically get you to about 1/10 of a torr. We're talking, we need a vacuum source that gets you 10 to the -6 torr or better. Okay, so very, very low vacuums. Very, very low pressures, I should say. Very high vacuum, very low pressure. And the reason you need that is because you don't want your ions running into any air molecules or anything else really, because they can tend to react with those types of things. So you have to have a very high level of vacuum in your system. And so if we were to draw this out as a block diagram, what you would have is you would have your ion source. That would then be coupled to your mass analyzer. Which would then go into your detector. And then the signal from the detector would go to your data system, your computer. And this is where you would actually see your spectrum as a mass to charge versus intensity plot. Okay? And so all of this, pretty much so from about here over, depending on the system you're using, has to be under vacuum. Okay? So you've got to keep this under really good vacuum. You enter your sample in here. The sample gets ionized. The ions then move into the mass analyzer where they're separated by their mass to charge ratio, and those separated mass to charge ratios are then detected by the detector, which gives you the data that you see on the screen or on your computer screen. So all of this is what's necessary. Regardless of what technique you're using, you've got to have some type of ionization source, a mass analyzer, a detector, a data system, and a vacuum source. And so everything that we talk about in this particular set of lectures, you note that you're going to have those components available to you. So give me just a moment. I'm going to erase this and we'll finish up with some of the types of ionization that we have available to us here at the University of Southern Mississippi. So let's look at our types of ionization and what are some of the benefits of each type. So the first type that you're familiar with, which we actually don't have access to here, is electron impact. Also known as EI. Many of you probably learned this as electron impact, but actually it's electron ionization. So impact is actually a misnomer, and we should think of this as ionization because the electrons actually don't impact anything. We're using the wavelength of the electron beam to do this, so it's not a particle phenomenon. This is known as a hard ionization technique. It gives lots of fragments. You sometimes don't even see the molecular ion. The molecule will actually fall apart quite easily under electron ionization. And this works very well for low molecular weight organic molecules. And this is typically what you have in what's known as GCMS, or gas chromatography mass spectrometry. And so we do have some GCMSs on campus, and they all use electron impact type ionization sources. But again, you're going to be really limited to those low molecular weight organic molecules with these. Okay. In our labs here, we actually have access to what is known as electrospray. Ionization, also known as ESI. Okay, so electrospray ionization is actually a very useful ionization technique, and it is considered soft. It's a soft ionization technique, meaning that once the molecules become ionized, they rarely fall apart into fragments, so you get a very low level of fragmentation. In fact, you have to intentionally fragment the molecules if you want to, and you can do that. And typically when you're just running the ESI, as we call it, you get very few fragments. And you can actually determine things that are very high molecular weight. So this can, you're really not limited by the molecular weight of the molecule so much with this technique, because you can put a lot of charges on it. We'll talk more about that in the next video. But this is typically used for things like biomolecules, that are polar, or polar molecules. So you got to have a polar molecule. Biomolecules fit this bill quite easily. So things like proteins, peptides, very easy to analyze by electrospray ionization. Polar organic molecules can also be determined by electrospray ionization. The other technique that we have access to that uses the same instrument is called atmospheric pressure. Corona ionization, or APCI. And it is essentially the same thing as electrospray in terms of these things. It's a soft ionization technique, typically gives low fragmentation, can be used on high molecular weight molecules, but it is typically used for non-polar, so things that are more non-polar. So you can do biomolecules, things like lipids, which typically are less polar than the other biomolecules we talked about. But you can also do regular organic molecules or synthetic polymers with so-called APCI. And then the last technique that we have available to us is known as matrix assisted laser desorption ionization, or MALDI. Some of you may already used the MALDI instrument. The biochemists really like to use MALDI. It is also a soft ionization, results in low fragmentation, but has very high molecular weight capabilities as well. And so this technique is actually used an awful lot in synthetic polymers. So if you're interested in determining the molecular weight distribution or the molecular weights of your synthetic polymers, typically people go straight to trying to use MALDI because there are some advantages to MALDI over electrospray or APCI that we will talk about in the next video. So that's pretty much so what I wanted to get through for the first lecture for my time with you in this course. I want you, before we move on to the next set of videos, you need to read all of the papers in Canvas. So in my little module within Canvas, you need to read all of these papers before you go on to the next set of videos when they become available. I will assume when we're giving these videos that you have actually read all of those papers. And so next time when we meet, make sure you've read all the papers and make sure that you are ready to talk about the types of ionization. So we're going to talk about MALDI, we're going to talk about electrospray ionization, and we're going to talk about APCI. We're going to talk about the advantages and the disadvantages of each one of these techniques. We're going to talk about how these techniques can actually be hyphenated and coupled to other pieces of equipment. So for example, you can do liquid chromatography mass spectrometry with two of these techniques, but not with the third. And so there are advantages and disadvantages to each one of these techniques, and hopefully you will get an idea as to why you might select one technique over the other. So again, make sure you read all of those papers in Canvas, and I will see you next time. And I will also be sending out to each of you a list of available times when I might meet with each of you if you have any questions about any of the material that you're going over. Thank you.